CMake is an open source build system generator used a lot in software development. Rather than needing to know a build system like Make or Ninja, you can, in theory, just configure CMake to have it generate the required files for you. It simplifies the build process, and it's cross-platform too. Zephyr relies heavily on CMake during the build process. If it's not something you've seen before, it can be a little confusing, so we're going to take a look at how to use CMake independently first before diving into how Zephyr uses it. Let's jump in. Previously, we looked at Zephyr and made a simple blinking LED demo. Now we're going to start building up the different layers and subsystems used by Zephyr to give you a foundation to really start using it. The first of these systems is CMake, which is used widely in software and firmware development. CMake has a great reference documentation on cmake.org/documentation. If you click on the reference doc link, you'll be taken to this guide. We're going to be working with 3.22 since that's what the version of Zephyr we're using uses. So we're going to go to 3.22 here, and you can use this as a reference guide to understand all of the tools, reference manual, and what have you. Let's go into our Docker container and make a simple CMake example application. As we did in the first episode, I'm going to navigate into the Introduction to Zephyr directory, where I downloaded the repository for this course. I'm going to make sure Docker desktop is running, and then I'm going to run docker run --rm to remove the container when we're done, -it to make it interactive. I'm going to map ports 22 to 2222 and 8800 to 8800 so I can access them either from a web browser or SSH. I'm going to mount the local workspace directory to /workspace in the container and then turn that into my working directory. So make sure we use the tag env-zephyr espressive, assuming that's the tag you created with the Docker image. Let's fire this up. In a moment, we should have our server running. Feel free to access this from localhost port 8800, but I'm going to do everything locally from VS Code. Assuming you have the remote SSH extension installed, I'm going to connect to host. I'm going to go to my local host, the one that we set up in the last episode. That's going to bring up a new window here, so I'm going to resize this like so. It's going to ask for my password. I'm going to enter that. Wait a moment, it should set everything up, and it does take a moment to download and install VS Code pretty much every time with this container because it has to match my local version of VS Code. I'm going to increase the size here so you can see what's going on, and then I'm going to open Workspace from File. Let's go up to the root directory. There should be this Zephyr code workspace. We're going to open that. It's going to want my password again. And we should be back to where we were in the previous episode. We've got our two directories here, workspace and Zephyr. Let's close the things we were working on. And we're going to make a new application in here. Let's create a new folder. We're going to call this O2 CMake Demo. And in there, we're going to create another folder called include. This might be where you put your .h files. The directory structure is a little arbitrary. I'm doing it this way so you can see how CMake pulls everything in when we create that CMakeLists.txt file. In this include directory, we're going to create a very simple .h header file. We're going to create header guards so that this file cannot get included twice. And we're going to make a very simple function that just prints something to the console. Note that this isn't something unique to Zephyr. We're actually going to compile and run this on the local machine. We're doing this all through Linux, so no need to even have Zephyr installed. If you're running Linux and you have GCC and CMake installed, this should work for you without even needing a board. Save that file. In this demo, let's create a new folder called src for our source code. Let's create the source code for this library. We're going to include the standard input-output header file that's in pretty much most Linux distributions. That allows us to do things like printf to the console, and we're going to include mylib.h. Notice that I'm not referencing this by the path. So if I wanted to reference it directly by the path, I would either need to include mylib.h with or next to my .c file, or I'd have to do something like go up one, go into include, and then include it there. We're going to have CMake include all the includes from this directory so that if I just say include my file here, it doesn't need the absolute or relative path to know where to find that include file. CMake is going to handle that for us. I'm going to do the classic hello world and then carriage return and new line in case you're printing this on the Windows machine. Otherwise, just the \n is fine. And that's it for our source code. So save that file. Now let's make our main. So under source, let's go new. We're going to do main.c. We're going to include the header file for our library here. Once again, note that I'm not using the relative or absolute path to find that. CMake is going to help us find that. We're going to define our main. That's going to be our entry point, and we're going to just call our sayHello function. That should just print to the console. And then, like any good application, we will return 0, stating that there were no errors. Now, this is where the files and paths get very specific. In the main part of our application, or where our code is, basically the top level directory, we're going to create a new file and call it CMakeLists.txt. The spelling of this is very important. It needs to be in this camel case or Pascal case, because when we call CMake, it looks for this exact file with this name. The first thing we're going to do is specify a minimum CMake version. That's calling the function CMake minimum required using the symbol version and then giving it that required version. We're going to use 3.22 because that is what our current version of Zephyr is built on. If you dig into the Zephyr code, you can find that. To find this, I'm going to copy this. I'm going to search in our Zephyr source code, so find in folder, and we can see that, oh, it's actually calling 3.20. So I thought it was 3.22, but it looks like it's 3.20. So you know what? Let's make it match that. So I'm going to save that right now. And then I'm going to go to my main. Notice it's not saved here, so I'm going to save that. If you're curious about where these commands are coming from, go to our CMake reference guide. And instead of 3.22, because I just found that correction, let's go to 3.20. The commands I'm showing should be the same between those two versions. CMake does add versions later, but most of this should be backwards compatible. If you go to Reference Manuals, CMake Commands, you can find the CMake minimum required. These are pretty much all the commands you can use in CMake unless you define your own. So with this minimum required, you can read about how you can specify a version and you can specify a minimum. You can also specify a range, optionally starting with this 3.12. But let's just go with the minimum because that's what Zephyr is using. Let's go back to our files here. In some cases, you don't need to name a project, but I find it very helpful when doing things with CMake. All you do is call the project command and you give the project a name. In this case, I'm calling it hello_world. We're going to give it the version of our project. This is optional. We don't have to do this. In fact, these three parameters are optional, but notice I have to give the symbol version here, description, and languages. That's basically calling out the parameter names. The languages you put here help CMake understand what languages and how to work with source files. It also helps it do things like find the correct compiler. So if we go to our documentation, we go back. If we look for project commands, here it is. You can see languages, you can read about the different options. And while it is optional, you can see how it helps CMake understand what languages you are using. Back in our code, we're going to create a static library, and we're going to give it the target name of mylib. In our project command, we created this name hello world, and we can reference that later. A target is an output of the build process, like a module or a component. This could be things like executables for your application, a library, or something like an interface. There are others, but those are kind of the three main ones that you'll come across. If we go back to our documentation, you can see our add library here. And you can see that we have the option of saying static, shared, or module for our library. When working with Zephyr, we're going to pretty much always make statically linked libraries because they get compiled into the application code. So let's just go with that. Both shared and module libraries are linked at runtime. That's for things like shared libraries in a system, or when you load a module into the kernel, if you're working with something like Linux. We're not doing shared or module libraries. We're just going to stick to static libraries because that works for embedded systems. And this is supposed to be all caps based on that documentation, so let's go with that. Notice I'm breaking these out here, 1 parameter per line, so you can easily see what I'm doing, but you will find cases where people will write things like this, and it means all the same. CMake does not care about lines. You'll run across a lot like this. I find it a little easier to read when you put 1 parameter per line, but feel free to write it however you want. Just note that we do need to open and close the function with these parentheses. We also want to include the header files so that mylib, the mylib.c source code, knows where to find that mylib.h header file. And this is the more or less magical command that does this. Target include directories, we tell it the target, in this case mylib, and we're also going to state public. That adds the directory to the search path for anything that links to this library, which includes our main application. So by doing this, when we include mylib.h in mylib.c, and then we include mylib.h in our main.c, this allows mylib.h to be seen by that main.c because we are linking main.c, our application, to this mylib library. Next, we're going to create an executable target, and we're going to use the same name as the project name. You'll notice that I'm using some variables here, like CMake current source directory. That's something that's built into CMake, and CMake knows what that is. That means the current directory. So within the CMake demo directory, it knows to go from there into include. So it's basically doing a relative path into this include directory. And then it also knows what project name is. It sets this variable whenever we call the project function here, and it's the name that's given as the first parameter in the project function. So we name the project, and then we can use that throughout when we want to use that name, for example, as another target. And in this case, we're creating an executable target. You don't have to do this. You could name it app or whatever you wanted, and that would be the executable target. But I like to keep it the project name so that the executable gets named that when we build the whole project. Now that we've built the library, or told CMake that we want to build the library, we set up the include directories, and then we created an executable target. We want to link the library to our executable. To do that, we need to use this target link libraries command. We're going to pass it in the project name, or the target of our executable. So if you used app here, but once again, I like using the project name that we set up. Private means that the library is only usable by this particular executable. It's not exposed to other targets that depend on this target, in this case, the application target. And then we're going to give it mylib, which is the target name that we set up here for the lib. This has nothing to do with the C or .h file names. I just named them as the same thing. So if you said mylib1, you would need to name this mylib1. That's just the arbitrary target name that we created. So let's change that back to mylib, and we should be good to go. So let's save that. And let's come down here to our terminal. Remember, if you don't have your terminal, you can go to the terminal menu and say new terminal. It's going to ask you for a working directory. Workspace is fine. We're going to go into our apps and then O2 CMake demo. If you look at the files in here, it should be the source code, the header files, and the CMake lists file that we created. Normal CMake usage is something like this. You'll see make dir build directory. So that will create a build directory for us. You go into that build directory, you call CMake from within that build directory, but you give it the context of one directory up. When you do that, CMake will run, and it will write build files to this directory. So I'm going to bring this up so you can see what's going on. I'm going to refresh this, and then I'm going to expand this so you can see that CMake created these boiler templates. You'll notice that it created, by default, a make file. And this is a pretty involved make file for such a simple application, and that's because it's generated and it tries to handle all sorts of different libraries, configuration, targets, executables. It pulls all of that in from CMake lists. Remember that CMake is a meta tool used to build files. So make is a build system, and CMake helps us make files or Ninja files or anything for those various build systems. Because this is make, and we have make installed on our system, we can just call make. It's going to read in that make file, and it's going to build that application for us. It creates this hello world target. So with hello world created, right here, that's an executable. We can go ahead and execute that. Once again, you just see hello world. If you want to build again, say you make a minor change, you can just call make. But if you make major changes, you need to get out of this directory, and you need to remove this full directory, which is rm-rf build. Now you would do the whole process again of creating that build directory, going in there, and calling CMake. Since CMake version 3.13, we can actually specify the build directory rather than having to create it, go into it, and then specify the context. That's one up. We can call CMake-S, which is the path to the source folder. In other words, the context. We want to use the current one, so instead of ... we would just use dot since we're in the directory with the CMakeLists.txt file. And then we can call -B and give it the build directory that we want to create. In this case, we're just going to call it build. With that, you can see it creates the build folder for us. Like last time, you can go in there and call make, but CMake includes a -- build process that will figure out which build system we want to use and call that build system. We're going to give it the folder to go into. So CMake is going to go into the build folder, see that we have a make file, and then call make from there. I find this a little easier than creating a build folder every time, but you will still come across many examples and demos that use that older method of CMake. If we take a look in the build folder, sure enough, it created hello world, and we can run hello world again. Like last time, we can just go ahead and get rid of that build folder when we're done. If you type CMake-H, you can get a list of generators. These are your available build systems. And CMake uses a generator to write out the configuration file in order to build your project. By default, it's using make and the associated make files. But because of Zephyr, we have Ninja installed. So let's try using Ninja. We got rid of our build directory. We're going to do CMake-S for the source code. Remember, this is a capital S. We're going to give it the context of the current directory. We're going to say, do everything in this build directory. And then we're going to do -G for the generator. And we use the name given here when we listed them. So just call Ninja. Unix make files is default, but if we specify Ninja, it should use Ninja for the build system. So go ahead with that. Let's refresh our files up here. And sure enough, instead of a make file, it created build.ninja. So if you're familiar with Ninja, and I am not, this is Ninja's equivalent to a make file, where it tells the build system how to build our project. Back in our terminal, as we did last time, we can call CMake-build, give it the build directory, and it will figure out which system to use. Although it's not -build, it's --build. Let's try this again. There we go. Ninja was called, and let's look inside of our build directory. Sure enough, we have hello world that's been created for us. We can call that, we get hello world. That shows that we used two different build systems with CMake. And let's clean up, we will get rid of that build directory. If you'd like to dive more into CMake, there is a great free online book called Modern CMake. It's at cliutils.gitlab.io/modern-CMake. The author does a great job of walking you through several examples on how to create CMake files in order to build your project and helping you understand what they mean. Zephyr extends CMake to include a number of specific functions around Zephyr to help make Zephyr projects. If you go to the Zephyr documentation, you can learn more about the CMake package that it uses. If you want to see the source code for that, go to CMake modules extensions.cmake in the Zephyr code. Let's do that from our system here so we can see it more or less locally. So we go to CMake, then we go into modules, and then we go to extensions.cmake. Let's bring this terminal down since we don't need it. You can get an idea of all of the custom functions that Zephyr creates for CMake. These include a lot of the Zephyr underscore or Zephyr underscore library type of stuff. These are not generic CMake functions. These are unique to Zephyr, There's a lot of good documentation in here if you want to read it. It's not coloring the syntax for me because I don't think I have that extension installed, so feel free to install the CMake extension, or you can view the source code right from the Zephyr repo. Feel free to scroll through this and look for these types of comments that talk about what the custom functions do. I could not find reference documentation for those custom functions in the Zephyr project's reference documentation guides. I put a request in for that, so we'll see if Zephyr adds that. But for now, with that in mind, let's get rid of our example here. Let's go look at our Blink example. If you go into CMakeLists.txt, you can see that this mostly looks the same as what we were doing. The minimum required version, we have it as 3.22 here. You could probably update that to 3.20. Find package is a base CMake function. We give it the Zephyr base directory. That should be set in environment variables whenever we set this up. So if we do print env and then look for Zephyr, you can see Zephyr base is set as an environment variable to op toolchains and Zephyr, which points to this directory right here. We then give the project a name. We didn't put the version or description because those are optional, but Blink is fine. And then we locate the source files for the application. Notice we're using the target sources function here. We give it app as our target. One of the things Zephyr does whenever it finds this package, which includes all of those extension custom functions that Zephyr creates, part of that, it automatically calls add executable, app, and then some other parts to it. So it creates this app target for us automatically whenever we find package in Zephyr gets included. Whenever we want to add things like libraries to our main executable target, we have to use this app target name. So we're going to get rid of that. Zephyr automatically handles linking the various libraries that are found within its source code using the kconfig system, which we're going to look at next. CMake might handle bringing all those together, but that's all done within Zephyr and we don't need to worry about it. If you want to add custom libraries, then yes, you will need to build them and link them in your main CMake lists file in your application code. Once we have that done, I'm going to go ahead and save this, even though I didn't make any changes. We're going to come down here to the terminal. We're going to back out and go to Blink. We're going to use this Blink example again. We have a build directory from last time, so let's remove that. And previously we used the west command. West is another one of these meta tools that can do things like call CMake for us. So how would we build this project without using west? To do that, let's call CMake manually. First, we'll specify the generator, which is Ninja, like we did in the previous example. Zephyr also looks for this board variable to be set. To do that, we're going to do -d. That tells CMake we're setting a variable, and then the variable name board equals ESP32 S3 underscore devkitc, which is what we set last time. Then we have to give it the processor or module and the actual CPU we want to target, in this case, the ESP32 S3 and the Pro CPU on that chip. If you remember from last time, we also needed to pass in our overlay file, which tells the build system how to connect the pins together using device tree, which we'll cover later. In this case, because we're not using west, we can just say -d directly without doing that -- because we're now passing parameters directly into CMake. We're going to use DTC overlay file. This is another specially named variable that Zephyr looks for in order to set this overlay file so it knows how to build that device tree, so it knows how to connect all of our hardware together. We're going to do -B. We're going to specify a build directory. Remember, we just deleted that. It's going to create a new one for us, and then -S and give it the current directory. West makes this a little bit easier for us, but if you want to do things manually with CMake without relying on west, this is another good way to do that. It looks like everything's been written to the build directory. Sure enough, this is exactly what we were looking for. Notice that it is bigger than our CMake demo before I deleted that build directory. This has a few more things in it because we are using Zephyr. This find package says include the Zephyr package, which includes a lot of special things from Zephyr. And that tells Zephyr to do things like oh, go ahead, create this Zephyr directory, bring in all the things from kconfig, our kernel, various libraries, and go ahead and build our device tree file, which connects all of our hardware. If you look, this is all of our hardware configured in a device tree. We will look at this in further detail in a later episode. Now we have everything we need to build this application. As before, we can say CMake --build and point it to the build directory. That will actually build the application. When we used West, that both created that build folder, updated any files that were needed if we didn't blow it away using the pristine flag, and then also called this build command that went ahead and built the project. So now in Zephyr, let's update our listings here. We should have our zephyr.bin and zephyr.elf. These are our binaries ready to be flashed. Your challenge, should you choose to accept it, is to modify this blink example and basically combine it with what we did in the CMake demo. You should create a mylib.c that has something like printf, or in your case, you probably want printk because that's a little more efficient for things like Zephyr, but in my experience, printf also works. You're going to put that in the blink directory in, say, your source, or maybe you want to create another lib folder, wherever you would like. You also need to create a header file, and you need to include it in your main.c. Your goal is that whenever you blink the LED, you should be able to do something like say hello, call your function, and it prints whatever you would like to the console. For example, hello world. Don't forget that you will also need to update the CMake lists here in order to build and link that library. So in the end, you should have something like this solution that I'm not going to show you exactly how it's done, but I've got a lib here with my include and source. Notice that I have another CMake lists inside of this library directory. A hint is that you can actually include other CMake lists from your main one, so you can create recursive CMake lists if you so choose. That's one way to do it, and that's how I did it in my solution. But so long as you create a separate library with your own source code that prints to the console, you're good. Let's give you a demonstration of this working. So I'm going to bring up my console. I'm going to start a new terminal here. Let's zoom in. I'm going to navigate to my Introduction to Zephyr repository. Don't forget to activate your virtual environment so you can use the Python scripts like ESP_tool. Then I'm going to do that very long flashing command using ESP_tool to connect to port 7, auto-detect my chip, reset the board before and after the flashing, and then flash that zephyr.binary, in this case from the solution, but from whichever folder you have created for this challenge. Once that's done flashing, I'm going to do python-m serial.tools.miniterm to use the miniterm program that's part of PySerial, connect to, in my case, COM7, but that might be /dev/tty, something for you if you're, say, on Linux, and then give it the baud rate of 115/200. And with that, instead of showing the LED state, although you might still show the LED state, but I'm going to print that string from the say hello function every time the LED blinks. If you see something like this, and you set up the library correctly, you know you've done the challenge right. I hope this helps you get started using CMake in your own projects and understand how it's used in Zephyr. Next time, we'll see how Zephyr has adopted Linux's popular kconfig system to enable and configure different parts of software.